Hi, let's design a URL shortener, and this will scale from one user to 1 billion request. So imagine I give you a server and I say build me a URL shortener. You have a one developer, one server, one database, and maybe 100 users. Pretty easy, right? So you can create an API, store the URL, generate a short ID, and redirect the user. Done. But now I have changed the requirement. Instead of 100 users, we have 100 million users, and instead of a few requests, we receive thousands of requests every second. Now your original architecture start breaking. The server gets overloaded, the database become a bottleneck, the system becomes slow, and eventually one server simply is not enough. So how would you design this system? That's exactly what we are going to do in here. We will start with the simplest possible URL shortener and then scale it step by step until we are dealing with the system that can handle massive traffic. And more importantly, I'm going to show you that why we are adding each component. Let's start. So what we are building, before writing any code or drawing architecture, we need to understand the requirements. Our URL shortener basically needs two main operations. The first one is a user gives a URL, long URL, and we generate a short URL. For example, a user can have example.com/product/category/ something 1234, and in the short form we will have like short and maybe .ly and some small id. So this is a really small URL. And the second operation, when somebody visits this URL, we have to direct to the original URL, that was the long URL. So we have two main APIs. The first one will be a create short URL. This will create a short URL. Maybe let's name this maybe shorten, and this will give you a response in which the URL will be a shorter one. And then we have to redirect this URL to the main server, and that's basically our entire system. So our first architecture will be, let's start with the simplest architecture possible. We will have a maybe client, then we have a backend server, let's stretch this, and then database. I cannot find this. Database, and that will be it. The user send a post request to this shorten URL, and our backend generates a short ID, for example something AB or some gibberish ID. Then we can store this in the database, and later when somebody visit this URL, this gibberish URL, it will get the original URL and we can redirect the user. Very simple, and that's exactly how we should start. And how do we generate the short ID? Basically, Now we have a interesting problem. How do we generate ID? For example, this is something like this, not that long, maybe this one. So our approach is to generate a unique ID, a numeric ID. For example, 1 2 3 4 5 6, and then we can convert that number into something like base 62. For example, base 62 means we use like A to Z and A to Z in small, or 0 to 9. That's 62 possible characters. So instead of exposing 1 2 3 4 7 8 9, we can encode it into a much shorter string, something like 8M3K. The important property is the generated ID. It should be unique, because if two different URL get the same short ID, we have a collision and our system will break. So our first challenge is generate unique and short identifiers. For a simple system design, we could use a auto incrementing database ID and encode it. There are also other approaches like random ID, UUID based approaches, and distributed ID generators, and also hashing. But don't overcomplicate this yet. Now let's scale it. Our system works. Let's say we have 10 users, 100 users, and 10,000 users, no problem. But suddenly we have 1 million users. Our single server is receiving more and more requests. CPU uses increases, memory increases, and response time start increasing eventually. And our server becomes the bottleneck now. What can we do? We can make the server more powerful. This is called vertical scaling. Instead of 2 CPU cores, we buy 16 CPU cores. Instead of 4 GB RAM, we use 64 GB simple. But there is a problem. There is a physical limit to how powerful one machine can be. And there is another problem. What happened if this one server crashes? Everything goes down. So instead, let's add multiple servers. That is horizontal scaling. So basically we will have server 1 2 3 4, but there is a problem. Who decide which server receive the request? We need a load balancer here. And the load balancer distributes incoming request across our 4 servers. For example, request 1 goes to server 1, request 2 goes to server 2, and so on. So if one server crashes, the request will go to another server. The load balancer can detect that, and it will flag like it is unhealthy and stop sending requests to it. Now we have a scalability problem, and not problem actually, we solve the scalability actually and availability, but we created another problem. The problem is the database. Now we have 4 application server, and but all of 4 server are talking to the same database here. So all 4 server are talking to the same database. So our architecture looks like load balancer, then servers. Let me put this here and put servers here. And they are calling one database. As the traffic increases, the database start receiving more and more requests, and eventually the database become our bottleneck. So let's think about what our URL shortener actually does. We have 2 operations: create the short URL, redirect the short URL. For example, someone creates a short URL once, but that URL could be clicked million of times. So we have a huge number of reads. This is where caching becomes extremely useful. So add Redis cache just before the database here. So client will call to the load balancer and application server, then the Redis, then the database. When someone requests the sort URL, we will first check the Redis. Does Redis have it? If yes, we will immediately return the original URL. We don't need to query the database. This is much faster, and we are also reducing the database traffic. If the URL is not Redis, then we query the database and then we store the result in the Redis. So next request can be served from cache. This is basic cache aside pattern. We can discuss about Redis in a separate video, how this is very fast, how actually Redis works behind the scenes. But now we have a new problem. Let's say the URL exists and it points to, for example, example.com page 1. We store that in Redis. Now the user changes the destination to for example, the URL has been changed, right? But Redis still contains the old URL. So our application might continue redirecting users to old URL. This is called stale cache data, and this is where cache invalidation becomes important. When data changes, we need to invalidate or update the cache value. This is great example of something I mentioned in the previous. Every solution introduce new trade-offs. So Redis makes read faster, but now we have to think about the data consistency. So what if we have millions of database records? Now imagine our URL shortener has 100 million URLs. Our database is getting huge. Our database might eventually become difficult to scale. One option is database replication. We can have primary database and read replicas. Write goes to primary and read goes to maybe replicas. For example, it can have a replica, and this is primary database. So reads can go to the replicas. So create short URL will go to primary database, and like this, and this can go I don't know how to bring this here, but anyways, this can be write and this can be read. So this is helpful to scale read heavy workloads, but again there is a trade-off. Replication is not always instantaneous. There can be replication lag, so we need to understand our consistency requirements. What if the database become really huge? Now let's imagine we are dealing with a billion of URLs. Now the database instance might not be enough. So we can consider sharding. Instead of storing every URL in one database, we distribute the data across multiple nodes. For example, database 1 will have A to F, database 2 will have G to M, and database 3 will have N to S. That's just a simplified example. In reality, we would usually choose a sharding strategy based on the access pattern and distribution of the keys. The goal is distribute the workload across multiple machines. Now instead of one database handling everything, multiple database shares the load. And what about a massive number of requests? Now let's imagine our URL shortener becomes extremely popular, maybe 10 million requests per second. We don't request per second. We don't want every request hitting our application server and database unnecessarily. So our architecture might now look like client, load balancer, application servers, then Redis cluster, then database cluster, and potentially sharding. Now we have much more scalable system, but there is another important question: what happens if entire data center goes down? So we can have multi-region architecture. if we are operating at a global scale, we might deploy our application in multiple regions, for example US, Europe. Instead of every user send request to one location, we can route users to nearby region. This reduces the latency. But now we have another complicated problem: data synchronization between regions. If a URL is created in basically in US, how quickly it should be available in the Europe? Do we need strong consistency? Can we tolerate eventual consistency? Again, there is not one universe answer. It depends on the requirements. What about analytics? Now let's say our product manager says, can we show how many times each URL was clicked? Easy, right? We could update a counter every time someone clicks, but imagine 10 million clicks per second. If user request platforms a database, right, our database could get destroyed. So instead we could make analytics asynchronous. The request happens, we redirect the user immediately, and at the same time we can publish an event, something like user clicked, and that event can go into Kafka messaging queues. So the background consumers can process those events. One service can calculate total clicks, another can calculate like click by country, another can calculate clicks by device, and so on. So that's the power of the asynchronous processing. So now what is our final architecture? The first request will come from the client, then server, then database. Very simple. Now we have gradually evolved it. Our architecture could now look like client, then let's rename this to client, then the load balancer, then the application servers 1 2 3, then the Redis, then the database cluster, and there can be Kafka after that. And there can be workers after that. These workers can do some operations, and there can be read replicas after that also as potential sharding. So we have gone from 3 boxes to distributed systems, but there are most important things. We don't start with all those technologies, we add them when we need. Let's review the problem. We had one server, problem too much traffic, solution horizontal scaling plus load balancing. Then the database become overloaded, the solution is caching and replication. Then our database becomes too large, solution is sharding. Then the analytics and the heavy operation were slowing down the request. Then the solution is Kafka and messaging queues, or the background workers. And if we need the global performance, multiple regions plus CDN where appropriate. So if an interviewer asks you to design a URL shortener, don't immediately start the drawing 20 boxes. Start with requirements. Ask how many users, how many URL are created per day, how many redirects can be there, do URL expire, do we need analytics. So these questions completely change the architecture. For example, if I tell you 10 users, 100 users, or you will probably don't need Kafka, don't need sharding, don't need Kubernetes, don't need microservices. So what is the big lesson here? So good system design is not about building the most complicated system, it's about building the simplest system that fulfills the requirements. So start simple, measure and find the bottleneck, then scale the bottleneck, and I think that's it. So that's how I approach designing a URL shortener. And we are going to let's say we are going to design something much more interesting in next ones, maybe WhatsApp or something. So I'll see you.